Hello, this is Professor Elliott, and today we were going to look briefly at the common source JFET amplifier. So you'll notice that the amplifier is self-biased, and we have resistor RG, that's the gate resistor. Okay, you've seen that before. We looked at the self-biasing. That's going to both increase the input impedance Zin as far as the AC goes, and it will also help maintain the gate voltage at 0 volts DC. So we have three capacitors. There's their functions, and we have a load resistor RL. And again, the assumption is that the reactance of the capacitors is sufficiently low over the frequency range of the amplifier as to render them as effectively short circuits. Okay. So this is the AC model. This is the formula for voltage gain. This is the transconductance ratio we're going to look at later. Okay, you might want to write that down. We're going to need it very soon. Write that equation down. Constant current model for the JFET. This is the output impedance. Okay, down here again, this is the output impedance. So again, this is drawn under the standard and usual conditions, where VDD is disconnected and replaced with a short, the capacitor is replaced with a short, and then you just simply redraw what you see, and that's it. Okay, and again, this here is effectively Z out, which is going to be this guy in parallel with this guy under AC conditions. Okay, a sample problem. Okay, so here's the JFET parameters. The IDSS of 6 milliamps, VGS off of -4. Okay, we're going to plot the curve as per usual using that formula. Okay, and this was done on graph paper. I know it doesn't look like it, but it was. Anyway, so we're going to plot the transfer curve, like, okay, all the way down there. This is the load line, which we determined by working out points 1 and 2. And again, look back at your notes or my notes on the plotting the load line of a self-biased JFET. And that'll give you information on how we arrived at that, but by this point we should have done it a number of times anyway. So the Q point, which is going to be right in the center. Let me get rid of that. Okay, the Q point is going to be right there. Okay, is where the two lines intersect. Okay, if you go back and look at this equation right here, okay, this is how you interpret or read that. So this is going to be the change in drain current, okay, which in this case is going to be about 2.7, and from here to the 0, this is going to be the change in gate to source voltage, which is about 1.88, and or I guess 1.38, that is, sorry. And anyway, so then we throw it into the equation, and we arrive at the voltage gain. So the voltage gain is simply equal to the transconductance ratio, GM, times RD, or if you prefer, it's just simply Z out, the output impedance. And the transconductance ratio is the change in drain current divided by the change in gate to source voltage. Okay, and that's how I got that right there. And for unloaded means there's no load resistor, so I got a gain of about 5.3. Okay, again, this is just simply a ratio. If we add in the load resistor, then the gain is now 2.92. Okay. So you notice that the CS amplifier has a very low gain, and that is simply because the curve here is incredibly non-linear, so you don't want the Q point moving around too much. So by biasing it, the Q point roughly in the center of the curve, and limiting its movement to an approximately straight line area of the curve, then the output is reasonably linear. Okay, so that's about it. Check out my more information in my Professor Notes handout, but I hope this was useful to you. Okay, thanks for watching, and I'll catch y'all soon. Bye-bye.